Hello everyone, this is the second video for the beginner's guide for trapped ion quantum computing. And in the first video, we talked about how to define qubits in a trapped ion system. And we defined two kinds of qubits, which are optical qubit and hyperfine qubit. And in this video, I'd like to explain how to get the ions. In the last video, we used the we said that the hydrogen-like ions has a similar energy structure of hydrogen atom, right? So, but if the ion is attached to a metal, it can, for example, you just ionize a metal. If it is just a charged metal, its energy structure is not a hydrogen-like energy structures. It's not what we talked about last time. So in order to get this kind of energy structure, we have to have an independent ion, an ion which is detached from a metal, which is an independent ion. However, in nature, we cannot directly get independent ions, just like the molecules in the air. Yeah, there are oxygens in the air, nitrogens in the air, but no ytterbiums in the air, no barium in the air, no calcium in the air, right? So in order to get an ytterbium gas, a barium gas, we have to get it from the metal. First of all, we need a metal. We still need a metal, or we need a target. We need such a target. A target can be either metal or compound. For example, if you want barium, we can get the metal barium or a compound, which is barium chloride. If we want calcium, we can also get calcium or calcium chloride. Different kinds of. We have different kinds of target. And the next step is we need to get the atoms outside from the target. We need to hit the target and then get an atomic beam, atomic beam or ion beam, right? So there are only two ways to do this process. The first is to heat it up. We can use an oven. We can use an oven just like we use with a current, and then when the current goes through a resistance, it generates some heat and it will heat the target up. After the target is heated to a particular temperature, you can get atoms out. Atoms out. For example, this might be the barium atoms. There will be an atom beam going outside the target, and it goes outside. This is the first way, an oven, and if we use the oven, we can only use the metal. For example, the metal barium and metal calcium. We cannot use the compound because the oven cannot distinguish, cannot get the metal atom outside the compound. Yeah, so typically people just use the metal if using oven. However, another way is to use laser ablation. For example, we use a pulse laser, which the pulse should be short and use single pulse contains such high energy. We use pulse laser. When a strong pulse laser hits the target, the compound or the metal will absorb this energy and the ions can be get out. If we use this method is called laser ablation. Laser ablation. If we use this, the target could be either metal or compound. Either is okay. Either is okay. So in this way, we can get the atomic beam out. Get atomic beam. Yeah. So there's a question: how strong should be the current is? It's the current. How strong should we set the current? What is the temperature we want for the target if you're using oven Or if using a pulse laser, how strong the laser power should be. Typically, the stronger the power is, the stronger the temperature, the more atoms we will have, right? The easier we will get the atoms out. Is it a good thing? Typically, it's not absolutely right. Yeah, if the current and the power is too weak, and it might don't touch the threshold, and there will be no atoms out. But if the power is too strong, there are also some drawbacks. Yeah, if the power is too strong, we have many atoms, and most of them are useless. On the one hand, we don't need so many ions, also many atoms, and there is a severe problem. We might talk about it later. That we need electrodes to generate the electric field to trap the atoms, to confine the atoms. And in the electrodes, there are some conducting areas and isolated areas. So if these metal atoms might accumulate in the electrodes, and then it might change the electric field we have and make the electric field quite weird, not a classic, not standard field, which is very bad for the trapping processes. So, and the worst case is that if this atomic and these metal atoms deposit on the isolators, it might connect to, if it connects to conductors, then the two conductors will be connected together. It's very, and then they share the same voltage. You cannot individually set the voltages of each electrode. So it's a problem. This is one hand. On the other hand, yeah, you might think that if you have a strong power, it's bad for the electrode, but it's easier to get more atoms and get more ions and confine the ions, right? Absolutely not. If the power is too strong, after using some power to get the atom outside, to beat the electric potential of the metal and get the atom out, the extra energy will be transferred to the kinetic energy of the atoms, and the atoms will be very fast. For example, we can draw a statistical picture. This is the velocity of the atoms, and this is the number of atoms. It's just a velocity distribution function. If the temperature is low, if the power is low, then it might be here. However, if the power is very high, it might be here. It might be here. And the average velocity will be higher. And there is one problem. We will talk about it later. Here we just talk about how to generate atoms, and later we will ionize the atoms to become ions. And why do we want to get the ions? The next step is to confine the ions. We must be able to generate an electric trap, and then confine the ions so that we can manipulate the ions. Yep. So if the velocity is too strong, even if the atom goes too fast, it's harder to confine the ion. As for if a trap is symmetric, you have an atom in, no matter what the electric velocity is, it gets out. Okay, it gets out because of the conservation of energy. However, so how to trap the atoms? Ions, you must cool the ion down when it is in the trap. You must cool the ion down when it is in the trap. So we need to cool it down. When the velocity is too high, it's harder to cool it down. So we don't want a velocity that is too high. So simply, we might think of it in a simple way, that we can set a threshold. Maybe under the velocity threshold, we can cool it down. We can cool the atoms down, and the atoms are trappable, are possible to be trapped by the electric field. So if the temperature is very high, you just such a small fraction of ions that could be trapped. However, if the temperature is lower, there are more, a larger area, and there are more ions possible to be trapped. So typically, maybe the power should not be too high. So we need to balance. Okay, we need to balance. Not higher better. Okay, we need to balance. And if we compare the methods of oven and laser ablation, you will find that laser ablation has some benefits. On the one hand, the targets don't have to be metal. It can also be a compound. On the other hand, it will not generate too much heat. If you use oven, you heat the whole target up, and there was some additional heat transferring in the whole cavity. Sometimes we need cryogenic trap to trap the ions, because in the cold environment, in low temperature environment, the electric noise of the electrodes are smaller. It's better, and on the other hand, the vacuum can also be better. And yeah, the pressure can be lower. Okay, so we don't want the temperature to go up. However, if you use oven, the temperature goes up. But if we use laser ablation, the temperature don't go up too severely. Yeah, it generates less heat, and then it just hits a small region of the target, not hitting up nearly the whole target. So the laser ablation won't generate too much heat and won't cause the temperature to go too high. This is the benefit of laser ablation. And then this is the first step to get the atomic beam. Next step is to ionize, so that we can get ions, right? Currently, we just have neutral atoms. Every atom is just a metal atom, and it doesn't have a charge. We want a positive charge so that we can be confined through the electric field in the future. So now we'd like to talk about how to ionize. In order to do ionization, typically, let me just give you an example. For a terbium 171, an ion, this is an ion, it has 2 electrodes in the outer layer, and the ground state is this 1s0. So it has an ionization energy. So if we hit it with a laser like this, and with an energy higher than this threshold, it will be a ultraviolet laser, and then it could be ionized. This is a method, but it has one problem. What is the problem? Typically, for a natural ytterbium metal, it has several different isotopes: 171, 172, 173, 174, 176, etc. There are many different isotopes, and the energy structures could be totally different because they have different nuclear and quantum numbers. They have different I. So typically we want ytterbium 171 because the I equals 1/2, which is very ideal result, yeah. So that we can use the hyperfine qubits, and then can easily do the state initialization and the detection. The energy structure is not too simple, it's neither too simple nor too difficult, not too complicated. Yeah, it's an idea, but naturally there are some other isotopes. How to get the other isotopes out? If you don't get them out, after trapping, you will find that because they have a different illumination, a different wavelength of the transitions. Later we will see that if you use camera to see the ions, some of the ions are bright, they are what we want, for example 171, but there are some ions that are dark, they could not be illuminated by the laser. They might be other isotopes. So we need to purify and get the isotopes out. So there are typically 2 ways to get out other isotopes. The first way is for the target. You can do the purification of the target itself and make a purified ytterbium metal. This is the first way. The second way is to do the isotope selection during the ionization process. If we use this method, we cannot we can never, it's impossible to distinguish different isotopes. Because, the ionization energy is very near for these different isotopes. Yep, and the energy of the laser, the photon must be much higher than the threshold, so it's impossible to distinguish them. However, we can have another way. We can use another layer. We can have a so-called two-step ionization. A two-step ionization. We can use 1p1, this energy level, and this is 399 nanometer. This transition 399 nanometer, and this ionization energy of this is 394 nanometer. It means that we can use a 399 nanometer laser to excite it to this state. And there is a feature for different isotopes. This transition, the frequency of this transition varies. They are different, and the gap might be tens of megahertz, which is larger than the natural line width of this transition. So if the power of this laser is not too high, it's possible to have isotope selection through this light. Typically, if we draw, this is the frequency of this 399 nanometer laser, and this, if we just, for example, get the atoms here and illuminate the atoms with 399, we will see it. The atoms will have or go on this transition, and then they also have spontaneous emission, and the spontaneous emission could be collected by imaging system we built, and then we will see a fluorescence from the atoms, which is called atomic fluorescence, and this is atomic fluorescence. During the process of trapping ions, this is the first step. If we see the atomic fluorescence, it means that there's no problem with the target, and the laser ablation process and the ionization process. It is the first step, and if we scan the frequency of the 399 laser, we can see several different peaks, which corresponds to different isotopes. And with scanning, we can see multiple different dips. Sometimes we see fluorescence, sometimes we don't see them. And then we need to set the frequency to the frequency we want to get the isotope we want. Okay, to get the isotope we want. And then we just excite. Then we will be able to just excite Yttrium-171 to this state. And then for the second ionization process, we can use any laser which has a wavelength shorter than 394 to ionize it, the Yttrium-171. Typically, we just use 370 because we use this for the cooling. And this is just a laser for the transition of S and P for the yttrium ion. Okay, for the yttrium ion, so we'll just use 370. Typically, use 370 for the second step of ionization. So this is the ionization process and how to do the isotope selection. And the next problem is how can we shed the 399 laser on the target, on the atoms. There are multiple different directions. For example, we might have this direction, 399. Is it okay? Yes, it's okay, but there are problems, which is called the Doppler effect. The atoms are going towards this direction, and the atom and the light are going towards each other. So it will face Doppler effect. the atom will see a higher frequency compared with in the lab, compared with standing in the lab, right? So the atom will see a 3 nano laser with a higher frequency. And because of the atoms have different velocities, right? They have a velocity distribution like this. So different ions with different velocities experience different frequencies of the 3 nano laser. It means that this line could be broadened, and the dips, the peaks of different isotopes will no longer be resolved. You'll be unresolved, and then you will be no longer be able to differentiate different isotopes. I cannot do this. So it is not appropriate to get the 3 nano laser in this way. So the better way is that the 3 nano laser goes in this way. It goes in this way. Not parallel, but but with a 90 degree angle, so that the first order Doppler effect could be eliminated. And this is a better choice. Okay, this is the content of this video. Okay, we talked about how to get the ions, okay, and just get the isotope we want. And then in the next video, I will talk about how to confine the ions. We have some ions, have atoms, and using the 3 nano laser, these are ions now with a positive charge. And then we want to trap the ions. We need a trap. We need some electric potentials to confine the ions. And then finally, we can use the ions to do something we want, something interesting, something to do the quantum computing. Okay, yeah, so this is all of the contents of this video. Thank you for your attention. Bye bye.